Okay, graphing radical functions. We know what radicals are. We need to just remember that functions are relations that have no repetition in the domain, is how we talked about functions, which is why when we look at the family of functions we're going to be looking at, which is the family of functions defined by this rule with the parent function, well, since the rule is f, we'll say our parent function is g. Our parent function is just square root x. The domain for this is 0 to infinity. The range is going to be the same thing, 0 to infinity. Now, the reason this works out that way is if we graph g, we want to plug in numbers that are only perfect squares just to make our life a little bit easier. So when we go to graph g, I'm going to plug in 0. I get 0. So I plugged in 0, I get out 0. Plug in 1, I get out 1. Plug in 4, I get out 2. So that's going to give me a graph that looks like this. And that is g of x. That's the parent function for the family of functions we're looking at today. And you can see, if we're thinking about the domain, how far to the left will this graph get? On the horizontal axis, how far to the left do we get? 0. How far to the right? It's going to go all the way. So our domain is 0 to infinity. Range, how low do we get on our vertical axis? The lowest point we see here is again at 0. And how high is it going to get? It's going to keep going up. Now, you can see it's going to be going up incredibly slowly, but it will continue to go up. So then we think about our family, which is given here. We've seen these rules before. H gives us our horizontal shifts, K gives us vertical shifts, and A is going to determine vertical stretches, compressions, and if A is negative, then we're even going to have reflections over the x-axis. So here, we will graph square root of x plus 4, and with that you should be able to graph square root of x minus 4 on your own. So if we're going to graph the square root of x plus 4, thinking back to our family of functions, the rule from that previous slide, we can see that A is 1, so there's no stretch or compression. H is 0, so there's no horizontal shift. But K is plus 4 here. Which means if we look at our parent function, which is like this, okay, that is square root x, then y equals the square root of x plus 4, you're just going to take each one of these points and move them up 4 spots. 2, 3, 4. So we are here, and we are here. So that is y equals the square root of x plus 4. So when you go to graph the square root of x minus 4, that's just going to be here. Move every point down 4. For both of these, well, let's not do it that way. Let's say up here for y equals the square root of x plus 4, my domain is still 0 to infinity. There was no horizontal shift, so my domain should not be affected. My range now, though, since I've moved up 4, my range is 4 to infinity. Down here for minus 4, the domain still 0 to infinity. The range, however, now is negative 4 to infinity. Here, now you can see the only transformation we're dealing with is a horizontal shift. On this slide, I am going to ignore this one. We're going to look at y equals the square root of x minus 2. We know that our parent function, square root of x, has a point at the origin. This tells us that we've moved to the right 2 spaces. So I'm here. We know that our parent function would have a point at 1, 1. Move that to the right 2 spaces. So So we're here, and we know that our parent function would have a point at 4, 2. Move that to the right 2 spaces, and we are going to be here. There. So there's the graph, y equals square root of x minus 2. For this one, the domain has been shifted to the right 2. The range, however, has not changed, so it's the same range as our parent function. Here, we now have a horizontal shift, a vertical shift, and a vertical stretch. So let's start with the end of the graph. If you've noticed with all these graphs, there is a spot at which they just stop. So in the parent function square root of x, that's the origin, because it just stops here. We go from here, going forever and ever and ever to the right, and forever and ever up, but it just starts here. That's the point we're looking for. Since we have a horizontal shift and a vertical shift, it is left 1, down 2. So this is the starting point of my graph. Now, for my vertical stretch, we're going to pretend that this is the origin. If this were the origin, then my next point would be at 1, 1. But we're stretching by 2, so instead of being at 1, 1, we're going to multiply the y part of our points by 2. So instead of being at 1, 1, we're going to be at 1, 2. We would be here. Again, pretending that this is the origin, my next point I would use would be 4. 1, 2, 3, 4. And it would be at 4, 2. But since we have a vertical stretch by a factor of 2, we're not at 4, 2. We're going to be at 4, 4, which is going to be here. There is my graph, y equals 2 root x plus 1 minus 2. There was a horizontal shift, so my domain now is negative 1 to infinity. There was a vertical shift, so my range is negative 2 to infinity. Here, this is basically a calculator practice problem. We want to put in y1, 4.5, and we want to put in y2, the cubed root of. Now to put this in the calculator properly, you have to do 3x in parentheses divided by 4 pi in parentheses, like that. And even some of your calculators may not do that radical sign this way. It may give you a really skinny radical sign and a bigger set of parentheses around the whole thing. The main point is this needs to be in parentheses, the 3x, and the 4 pi needs to be in parentheses, so that order of operations is done correctly. When you graph this in your calculator, you are going to have to mess with your window a little bit, but once you get there, you're going to have a line at 4.5, like this, and you're going to have your cubed root graph, which is going to look something like this, and you're going to have to try and find this point of intersection. That's what we want to do, is find the intersection point between y1 and y2, noticing that to put it in the calculator instead of v I use x, and it's that x we're looking for, and if memory serves, it rounds to 382 inches cubed, because they are asking for the nearest cubic inch. And so you are going to have to make sure your window goes all the way out far enough that you're going to be able to see this point. Here we want to take the square root of 4x minus 12 and rewrite it to fit this form we had for our family of functions. The way we do that is in the radical, factor out of 4. Our properties of radicals lets us say that's root 4 times root x minus 3, and root 4 is 2. So now it is in our form here, where a is 2, h is 3, k is 0, so there's no vertical shift. We have a vertical stretch and a horizontal shift. But that's what they mean by this wording. How can you rewrite it so you can graph it using transformations? They're saying rewrite it so it looks like this. The next thing we're going to talk about is the family of functions that has the parent function cubed root of x, which we saw this kind of in that word problem we did. The family is going to have the same exact look as the square root family, just with cube roots. So if we go to graph this, the cube root, no, it's supposed to go right through the origin. Being a perfectionist, so it's going to go through the origin. Cube root's going to look something like this. So we're not going to go into detail on this because the process of graphing these is exactly the same as square roots. It's just now you have this parent function as opposed to our square root parent function, which was just here.